All right, so here's the plan for today. I've got up here. I've signed into an account with fresh. Uh, all of the Project Euler problems are not yet solved. Project Euler, if you want to check it out, you can make an account for free. It's pretty neat. It has a lot of these problems. The first page here are all ranked pretty easy, so if you check these out, they'll seem pretty simple. But if you keep going through, there's just tons and tons of problems with all kinds of difficulty levels and uh, with all kinds of different topics and stuff. We're going to just start from the beginning, at least for today. Maybe later on in this project, I will skip ahead to other problems. But today we're just going to try to solve some of the early ones because that's like it's like a level 2 version of Hello World. We're just going to make sure we can do some computation. So our goal for today, if we get this done quickly, we'll keep going, obviously. But our first goal here is to I'm going to shoot for trying to get at least one problem done. And the reason that's, I think, a good first goal is because that's going to mean I have to like get all the I've get used to just the basics of like the flow of how this is going to work, which I'll explain a little bit more what I think that's going to be. But I'll come back here and read the details of this problem again in a little bit. But it's asking us to find the sum of all the multiples of 3 or 5 that are below 1,000. So we're going to do that, but we're going to do it in a way where the computations that need to get done. In fact, you could solve this on paper without too much trouble, but we're going to solve it with the computer. But we're going to have all of the mathematical work, all of the stuff that directly computes this, be handwritten. And then the thing is, I don't want to have to write like literally everything that way. Calling printf, for instance, in handwritten assembly would not be particularly useful for what I need to like practice. It's not, it's a lot more bookkeeping and fiddling with the ABI of printf than it is actually getting my hands dirty a little bit on learning how to write like how x86-64 code programs look when they get written. So I don't really care to do 100% of it in assembly. So what I'm going to have is we're going to have some assembly code, which you can see I've got a little test file I set up here during my test stream to make sure that I could actually run the assembler. But I'm going to have to like figure out how to write the computations I need over here and get them to assemble. And they're going to get assembled into an object file. And then we're going to need another file. So I'm going to, well, first thing I'm going to do is actually clean up the sort of test files I set up and set up like our real approach here. So let me do that. Need one of these. I suppose I don't need to do that anymore. I have a new machine, so I don't need to worry about hiding anything. Everything on here has been sanitized for on stream. So yes, this can go away. I think that's it. Okay. So yeah, no changes left. So what I'm going to do is I'm going to get us set up with 2 files and see if I can just like do a hello world thing at all, where I have 2 files, one in C and one in, well, it's going to have to be in C++, but then one in assembly, and get them to link to each other. So let's try to do that. I won't worry about organizing this too much yet. So here's our Euler file. Just get this up and running. All right, let me get that added over here. Okay. Git bash Euler. All right, so for now, I don't need all of the old stuff for the code base. We can switch back to these commands some other time, but we just need build Euler and run Euler. I guess I do need a run here, so I'm gonna grab a copy of that. Don't need this one right now. Run Euler. So we'll just make an executable called Euler, and that will print out our answer if it runs correctly. And we'll just modify that in place for each problem. We're gonna use that more like the scratch space in which we can write down all of the code we need to compute something and then save the good bits and throw away what we don't need. So we're not going to try to archive 100% of the details of every solution, but rather all the stuff that we think is reusable, we will try to save that, and then we'll throw away anything that's kind of just like the incidentals of the problem to keep the code from getting too complex in like, you know, keeping around lots of code that it doesn't actually get run on a regular basis. Most of this is throwaway code because we're just doing it to get some data out. And once we've got the data, the code isn't useful anymore. So that'll be the approach for maintaining this code, is we throw things away liberally, but we occasionally point something out that we think is reusable and try to save that. All right, so let me see if I can... I'm gonna have to write that first. Build Euler. Let's look at the build main test as an example, because I don't remember all the details off the top of my head of how to use this version of the BLD system. Sure, we'll print the implicit options, and then we will compile this source file into this executable target. Okay, I should have an Euler CPP. So what did I get wrong here? BLD path. This looks the same. So why would it be not working? Load this. That's not working either. Windows. What has changed? This was all just working recently. Okay, we're gonna have to debug our ability to actually build first, apparently. That wasn't expected, but here we go. What went wrong? So that's just empty. Right. So I go into bin, BLD core. Source path is yeah. Load local ops. BLD params. There's our problem. I did not on this new machine get set up with the BLD system. That was a mistake. That's okay though. We can do that. So new machine, how do we set up? We got to do BLD init. Let me just see here. We're going to be doing git bash BLD bin BLD init sh. Okay, did that. There we go. Okay, well, it's a lot closer. LLD link command not found. Did I forget to install Clang on this machine? I did. Okay. Getting new machines set up with everything you need is not always easy. Gotta add that to the list of things I'm supposed to do. Install Clang. All right, so that's the first thing we're gonna have to do is get Clang installed so that I can actually link a program with the LLD link. I can't just switch to using link. There's a bit of a hidden downside in the build system I have here, which is that since it uses bash scripts, it thinks link is like a special operation. It doesn't interpret it as an executable. It doesn't interpret it as the executable, that Microsoft gives, and no matter what you do to try to call the correct executable, it just refuses to actually invoke that executable. So the only way to get something to link is to call something with a different name. So you can rename LLD link or use a shortcut to LLD link, I suppose, or to the Microsoft link executable. But I like to install Clang anyways. So let's do that real quick. Clang Windows install. WikiHow, how to install Clang on Windows. Wow. Clang development, Clang info download. Okay. This isn't what I asked for. Download page. Sources, pre-built binaries. Okay, this is where I need to click. AMD 64. x86 64. Where's the Windows? Win64. This is the one I want. If you're using Bash on Windows, does this mean you use the Linux for workstations? I don't know what you are asking exactly. I'm just running Bash scripts. There's nothing else Linuxy about it. I'm not sure. If Linux for workstations is like a thing, then I'm not using that. It doesn't sound like a thing I've heard of before. 64exe. All right, this is gonna take a minute, maybe. How's that? Yes, that's just for installing. I'll turn it down again though. I don't want it to be uncomfortable, but I'll usually not try to talk over it or at the same time as it. Okay, so we have Clang now, which means we should have, yeah, okay. So maybe now we can build, oh, but I have to relaunch 4Coder, and since 4Coder is launched in this, I'll have to relaunch this. That doesn't matter. And now I'm gonna have to set up Visual Studio again. Now I should be able to let me do one other thing if that's the case. Let's track down, how do you even, volume mixer. Bring that down. Jeez. I find those sounds unpleasant all the time. How's that? I can still hear it very clearly. So it's fine for me if that works for everyone else. Okay, we want to get going here. Yep. Okay. Project, can we build now? A lot closer. Ooh. Okay. It looks like LLD Link is now reporting issues in the PDB file, which is cool. Let's see if we can fix that, because that might have happened when we switched. Well, I don't actually know why that would have happened. Let's just fool around with it for a minute. If I get rid of this, what happens? I don't love that. Is that something we can fix or hide? LD warning procedure symbol record. There's something I can do about it if your OBJ files are busted. Function ID record. Okay, so a couple possibilities. That could be because this new version of LLD Link is more sensitive to things, or it could be because the new Visual Studio install has errors that old ones do not have. So what do I want to do? I want to try and install a different Clang and see if that changes anything. That will be the easy thing, and if that works, we're good. If I have to do a different Visual Studio, there wouldn't be any easy way to recover. So I think this was the one I was using previously. So let's try this one instead. Oh, okay. And that's like, there's nothing fancy going on here. I'm just building a very basic CPP file with Clang. I'm actually building with CL, but I'm linking with LLD Link, and I'm getting this. I guess the other thing I could do is try the trick of creating a what's the word I'm looking for? A shortcut for running Link with a different name. That way I could maybe call it without having to use the name Link here. Let's try this. Yes. I really don't care that much about which version I have. I just want it to kind of basically work. There we go. Okay, so probably they added error detection, which maybe it's actually better if I had it, but I don't want to have to fool around with figuring out how to hide it right now, so that's going to have to go on my to-do list for things to do in the future. Look into the new Clang error detection on PDB stuff. Okay, just writing this down. Okay. So if I can build main.cpp, then I should be able to build this. Gotta reload the project whenever you do that. Okay, so we have Euler CPP building and running. So the next trick is I wanna be able to call a function from written from the assembly file and link it into the Euler one. So what we're gonna have is like, let's see, let me start with, let's just grab everything from the code base real quick. We can trim it down. So I don't need temp wave or audio gen. I don't need wave format stuff. I don't need the wave parser. Okay, so that's what we'll start with. And then from there, I know I have something that does like extern C linkage. Okay, that's a good name for it. Okay, so I want something that's C linkage. We'll call it asmTest, and asmTest will return an unsigned 32-bit integer and have no parameters. Okay, so if I do that, now it doesn't link because it can't find the symbol asmTest. So now what I have to do is I'm going to come over here into my source folder, and we're going to add in Euler.asm. We need to give them different names so that they have different object file names. So we'll call this Euler, we'll call this Euler main cpp.cpp. How about that? And then this can be Euler asm dot, whoops, Euler asm dot, stop it, Euler asm dot asm. There we go. As I learned before, I need to put that in there. So then the build Euler script, instead of building the unit like I'm doing here, I'm going to need to do this a little bit more step by step. So let's look at what my commands are here. I want to do BLD compile. Compile because then I can get just the object file. And I want to compile this one. So that should give me something called Euler CPP.obj. then I need to call the assembler. So something I should do in the future is if I'm ever gonna, I should extend the build system to have an assembler option. That could become handy for stuff like this. Okay, it's on the to-do list. Let's do this by hand for now. So this is ML64. Let me see, ML64 source Euler asm.asm. Right, and then I pass that like a /s or something like that. /c. There we go. Okay. So I need to over here. That's gonna have spilled one of these out. That's fine. So I want to do that right here now. So source path Euler asm.asm /c. Also throw in other good stuff. I think I need to do it like this since we're in Bash now. And let's make sure that that worked. No logo doesn't seem to have worked. If I do it like this, what do I get? Yeah, it interprets that as a... Okay, so that isn't even an option. How do I get rid of that? Can you give me help? Suppresses copyright message. You say that. You say that, but does it need to go first? Is that what's going on here? There we go. All right. So after doing that, so this still is jumping out right here. So I'm gonna have to do like cd, I think it's called build path. Let me just test this out real quick. Build path. Yep, so that's the right path. I'm gonna have it change into that directory, build that, and then or compile that part, and then we need to link them. So we'll call BLD link, and that takes the output name, so we'll call it Euler source or obj file. So if everything else is working, there should be, so these are not real anymore. Should be an Euler asm and Euler CPP. Those are the two I want. So those two go in. And if I do it like that, okay, so it's progress, but we're still not actually linking because I still have this undefined symbol. So now the goal is to define that symbol inside of my Euler asm file, and then it should link into a program that we can run and see a result from. So let's see if we can do that successfully. The other thing I noticed though is I don't have, I have an Euler exe. I don't have an Euler PDB. Right, let me try this. I guess that makes sense because I'm not actually building an Euler.exe, but I should make sure that this is generating debug info. Let's go look at how that would need to be done. I'm done with this. Error messages, assembler overview, so assembler overview, why don't you hang out over there? Here we go. Debug info, use SHA, generate code view information. Okay, so that means we need a /zi for debug information. Okay. And then this should automatically give us debug info if we're in debug mode, so long as it's actually able to build an exe at all. So let's work on that part. What is the syntax here? I don't want to just guess. I feel like I could spend all day just fiddling. I want to like example to start with. Inline assembler, that's not going to help. Yeah, that I know, but where is my syntax for... Okay, let's try this. We're going to do... Oh, maybe this will have it. Conditional control flow, conditional assembly. No. All right, as an example code. .data, .code. There we go. Okay, let's try this. So I think what I need is asm test. Was there? I think it's tabs. So we need tabs there. No, I don't need any of this stuff. So all we need to do is, what is the comment syntax? Semicolon. Okay. Return a 42. So we want to move. Do we have any examples of? I'm not really familiar with all the stuff I need to be familiar with to get this going super quickly. Like I know I did a little research on the instructions themselves, but I don't know the syntax that Microsoft is using. It looks like it's going to be a little different. So I'm going to try to put it in EAX. So I think that has to be the first parameter. This is the... Oh man, I got to figure out what syntax this is. Syntax. Now, here we go. Operand list. Here we go. This is what I need to look at for a minute. No, it's not actually what I need to look at. Operand list. What can you tell me about operand? Most instructions use an operand list to specify the explicit source and destination operands. Most may contain memory references, registers. For moves and compare instructions, only one of the operands may be a memory reference. or references or constants. Can I get some example syntax though? Okay. Okay. How am I gonna do this? So I know this is not the AT&T syntax. So what are the? Let's do this. x86 64 assembler syntax. Yeah. Give me. Just give me some like example code somewhere. This is Intel or AT&T syntax. So okay, so this puts the destination first. Okay, got it. So we want to put into EAX from the constant 42. How do you encode constants in this syntax? So no, I don't care about these. These are all in the AT&T syntax. I don't want the AT&T syntax. Can I get? Here we go. This might help. Immediate. Here we go. Okay. So no $sign. Is that all I need to know? Indirect. Scale. Note that in the generalized indirect format, Intel SandX will compute base plus displacement for you, as the app codes really only allow a single intermediate displacement. You should do this yourself. So this just is the syntax to use these pluses here. Okay, got it. So let's see, can that build? Needs to be in a segment. Does that do it? Undefined symbol ASM test. Okay, so it still doesn't actually create an ASM test symbol for me. So I gotta figure out how you do that. How do you create a symbol? No. Segments. Data, yeah, so I got that. Scope. Let's read what these do. See if that has anything to do with it. Procedure, maybe that seems pretty likely. Yep. I will be curious about that. Okay, let's take a look at some of these. So let's see, proxy mark start and end procedure block called label. The statement in the block can be called with the call instruction or invoke directive. Okay, proc, distance, language type, label, proc, distance, language type, public, private, export, prolog, R uses reglist, parameter, tag, frame, blah, 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 statements, label, end P. Okay. Example 1, proc, frame, statements, label, end P. What is this thing here? I'll have to go read about that macro, but let's try this first. So, looks like what I need to do is proc here, as in test, end P here. So that should begin and end that. Can I skip the frame and just go? Hey, you've got an executable. Okay. And it doesn't run successfully. Ah, you know what I didn't do is I didn't return. Awesome. Okay. Let's try 100 times more. Great. Excellent. 10 times more. Okay, so that worked. So now we're ready to actually move on from just getting these things to link together and make a program. And we can go on to the part where we solve the Project Euler problem, I think. So let's take a look. Before I jump into this, I don't know if anyone's watching, waiting for a chance to ask a question or chat, but now's a good time. I'll take a short break to give a chance for chatting and also to rest for a second. Alrighty, let's dig into this one. So, if we list all natural numbers below 10 that are multiples of 3 or 5, we get 3, 5, 6, and 9. The sum of these multiples is 23. Find the sum of all the multiples of 3 or 5 below 1,000. So this part here is sort of giving you an example and give you a way to test your understanding and interpretation of the problem, disambiguate what the question or the actual direction is asking for. And then it tells you what you're supposed to do. Find the sum of all the multiples of 3 or 5 below 1,000. So we could just go in and write the loop that does that. But before we do, if with these problems, if we take a minute to sort of think about what's being asked for, we will generally find that we can come up with a much better solution. And after the first few problems, it becomes more and more necessary to spend some of your effort on the math side of it, coming up with some way to compute the answer that will be cheap enough that you can get it done quickly. And then even once you've got that, then you can go do the computing parts. You can't usually do them on paper. This one we could do on paper, but we're going to get into the practice just now of like doing a bit of math to find a cheap, easy computation that we can do to solve the problem, and then writing the amount of code that it takes to do that, and not diving straight into writing the code or trying to do the whole thing on paper, but just the usual case of doing some of it on each side. So find the sum of all the multiples of 3 or 5 below 1,000. Let's talk about that. This one isn't something I have to work out from scratch because I've solved some of these problems before, so I know how I would think about this one. But I will explain it real quick. So if we think about what it's asking, if I can write down some of the very small natural numbers here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and this will go on all the way up to 1,000. And then we're supposed to find all of these that are multiples of 3 or 5. So what we could think of that as is it's saying basically do a loop that starts from 1 and check each number up to 1,000 or less than 1,000, so up to 999. And if it's either a multiple of 3 or a multiple of 5, accumulate it, add it into an accumulator, and then the final result is whatever's in the accumulator. That's like the simplest way to think of it. So it'd be like, no, not 1, not 2, yes 3, not 4, yes 5, yes 6, not 7, not 8, yes 9, yes 10, not 11, yes 12, 13 no, 14 no, 15 yes, and so on. So, one way we could make this faster is to say, well, if instead of summing up or iterating all of these from 1 to 999, we just looked at stepping by 3s and then stepping by 5s and adding them together, we would have an issue, but that would mean a lot less iteration, right? We could do 3, 6, 9, 12, 15. And then if we did the 5s, we would get 5, 10, 15, and so on. Then what we could do is say, in the iteration during 5s, skip all of the ones that are multiples of 3. So if it's already a multiple of 3, we're double counting it. So that's one thing we could do. But we could take this even further. So this would give us 2 loops that are kind of different. And the next step what we want to do is see if we can take advantage of sort of the regularity of the pattern here. This is stepping up by 3s, this is stepping up by 5s, and if with a trick we can find an easy way to compute the sums here if we don't try to cancel out these 15s, right? But that's going to lead to another issue. If we don't cancel out the 15s by skipping them in the 5, 10, 15 and just use one code path for both, then we'll simplify the code and we'll have to figure out how to deal with the 15s another way. So what we'll do is we'll think of this as adding in this amount, and then subtracting out this. So this will be all the multiples of 15 because they'll get added in twice. So we'll subtract out all the multiples of 15 after doing the first 2 phases. Then it's just a matter of computing 3 numbers, the first sum, the second sum, and the third sum, and then adding the first 2 and subtracting the third one. So then all we need is a fast way to compute these. And we can do that with a little bit more math. So if we look at this first row, they're all multiples of 3, so we can factor out a 3. We can rewrite this whole thing like this. Plus 3 times 1, 2, 3, 4, 5, dot, 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 right? So these are going to get added together. This one here is plus 5 times 1, 2, 3, dot, dot, dot. And then this last one is minus 15 times 1 dot dot dot, right? Okay. So what's cool here is that now we have this, this, and this. If we ignore the multiplier on the left-hand side, those are all the same. Those are all the triangle numbers. Now, which triangle numbers they are, we don't know yet. But if we have a fast way to compute triangle numbers, then we can do this quickly. And I'm not going to take the time right now to derive it, just because I know it off the top of my head. But if anyone's interested, I can show you a useful way to remember this if you forget it, using a technique that I think is pretty easy for deriving it from scratch. But I'm just going to sort of write down the knowledge we have here, which is the triangle number of n is n times n plus 1 over 2. And that's that triangle number that gives us a sum where, like, if n equals 1, we get this guy. If n equals 2, we get the sum of these. If n equals 3, we get the sum of these, and so on. So it gives us this. Another way I could write this is it's the sum when I goes from 1 to n over I, right? It's like I'm just adding up each number from 1 up to n. And this is a very fast way to compute that, because you don't have to do, no matter how big n gets, you just have to do a finite amount, a bounded constant amount of computation here, right? So this is our fast way to compute it, which means we can rewrite all of this again. Let me give myself a little bit more space here. So our original sum now becomes 3 times the triangle number. Now we don't know which triangle number, but it's it's some triangle number. I'll call it S3 plus 5 triangle number S5 minus 15 triangle number S15. Okay. So we know this will be a function that's easy to compute. So now the question is, what is S3, S5, and S15 going to be? And the answer to that is just whatever number we get, like however many multiples of 3 there are below 1,000. So how many, what is the number of multiples of 3 that are less than 1,000, right? If we can answer that, that tells us what S3 is. And we can do that by just saying, so, if you look at 1, 2, 3, there's one multiple, 4, 5, 6, there's 2 multiples. So as this goes up, we're going to make groups of 3, and then you'll get up to like 997, 998, 999. That'll be a group. And then 1,000 will be hanging by itself. So what we've basically done is taken 1,000 divided by 3. We've broken it up into groups where each group has 3 elements. So 1,000 divided by 3, and then throw away the remainder, right? Round down. So this right here is how we compute S3, right? So we can do all of it now like this. Our answer should be whatever we get when we do 3 times the triangle number of 1,000 over 3, round down, plus 5 times the triangle number of 1,000 divided by 5, round down, minus 15 times the triangle number of 1,000 over 15, right? That should be what we need to compute. And all of this is reasonable thing to expect the computer to help with. It can easily do division with rounding down. It can easily compute the triangle function, which I guess that fell off the screen as I was scrolling. And it can easily do these multiplies here, right? So what we're going to want to do is first let's write the code that computes the triangle function. Then let's write the code that does all of this. I'm going to zoom out so we can have all of this on the screen at once. So we're going to write this function here, step 1, write this thing, and then step 2 will be to write this thing and return the result. So let's try that. Just because I can, I am going to do this in 64 bits, and I'm going to preemptively start declaring things that might be reusable just based on a gut feeling. I'm going to take anything that I think might be reusable beforehand. I'm just going to preemptively declare it into the C++ code. We might later on extract some things that I didn't preemptively do, or throw away things that I decided were extra clutter in the end. Ooh, you can use spaces, cool. All right, so this is gonna have one parameter. This is where I'm gonna need to look up, you know what, I might need to find myself a good reference here. There's my syntax. Let's look at x86-64 ABI. Okay, we want to figure out who the arguments are. This is the result register, frame pointer, first argument. Okay, yep, this will be good. So first argument register, RDI. Okay, so R tells us that it's the 64-bit version. DI is like the actual name of the register, basically. So we're going to say RDI is N, first argument. And then we're going to do, remember, we're computing n times n plus 1 over 2. So what we're going to want is, let's see if we can find a caller save register. First, miscellaneous register, call save. Okay. So if I frame call save, so if I'm interpreting this correctly, I can use a register like RSI, I think, as a caller save register. Since I'm not expecting a second argument, I can just trample what's there. And the caller isn't supposed to assume that I'm not touching RSI, I imagine. So we're going to move, or rather we're going to add into RSI. No. Okay, first we have to move into RSI whatever is in RDI. Then we need to add 1 to whatever's in RSI. Then we need to multiply whatever's in RSI by RDI. So we're getting here, we get RSI equals n, RSI equals n plus 1. Here we get RSI equals n plus 1 times n. And then we need to divide by 2. So let's see if I can remember how to do that. Do I have, this doesn't happen to have anything to help with, that's signed division, right? Let's see if there's, so this actually takes this amount here. Right. So calling the div instruction is a little bit tricky because it doesn't give you the parameters like it normally does. It doesn't let you pick anything. It puts its output into RAX, and it actually gets the input from RDX and RAX and puts these together. So if I'm interpreting correctly, the only thing, The way I remember it is that RDX and RAX are glued together. RAX are the low bits, so we need to clear RDX to 0. And then divide. Oh, you know what? We're dividing by a constant of 2, so we can do better than this. We can shift right. Yeah, if we shift right by Y immediate register. Okay. So I should be able to do shift right RSI 2. Oh, no, wait, 1. And that gives me RSI equals n plus 1 times n over 2. Right? But now I have an issue, which is when I return, I'm supposed to have my result in RAX, and I put it in RSI. But that's fine. I can redo this with just RAX being the accumulator. So RAX gets n plus 1. It gets n plus 1 times n. It gets n plus 1 times n divided by 2, and then I return the result. So let's test that. Triangle. Remember, when I need to declare this correctly now, n. Let's see. Give me the triangle number of 5. Like that now. Okay, what's the issue? Comma. Okay, I take it the mul instruction doesn't take 2 operands either. So what does mul do? This looks like 2 operands. Imul. Do I need to call imul? I probably do. Okay. Do we have one called mul? Or is it just, yeah, there, mul. So it says here only takes 1 operand. The result is stored in register AX, register pair, or register pair EDX, EX, depending on the operand size, with the high order bits of the product contained in register. If the high order bits of the product are 0, the CF and OF flags are cleared, otherwise the flags are set. In 64-bit mode, the instruction's default operation is 32 bits. Use of the rex.rret prefix permits access to additional registers R8 through R15. Use of rex.w prefix promotes operations to 64 bits. Yep. So it looks like it automatically uses AX as one of the operands when you're doing unsigned multiply. So one thing I don't know is what's the difference between unsigned and unsigned multiply? I would have thought they were the same. So let's just see what the internet says real quick. Mul versus imul. What is this all about? Bytecodes that are output. World, there were too many opcodes, so the Intel engineers were finding ways to extend the portion of the bytecode that specifies the operation multiplication in this case into the portion of the bytecode that encoded the first operand. This obviously meant that only one operand could be supported when executing the mul opcode, multiplication. They solved the problem by hard coding into the processor that the first operand would always be the EAX register. Later, processors supported bytecodes that were of multiple lengths, which allowed them to encode more data into a single command. This allowed them to make the IML opcode much more useful. There's an interesting parallel today with the IP addresses running out. Signed versus unsigned multiplication. Why are signed and unsigned multiplication different instructions? The whole point of 2's complement was that operations could be implemented the same way for signed and unsigned numbers. Even says specifically lists multiply as one of the operations that benefits. Addition and subtraction are the same, as is the low half of a multiply. A full multiply, however, is not. Simple example. In 32-bit 2's complement, -1 has the same representation as the unsigned quantity 2 to the 32 minus 1. -1 times -1 is +1, whereas 2 to the 3 equals 2 to the 64. Right, so an unsigned multiply, the high bits stay the same, but the low bits are different. So they are different if you look at the high bits, the things that indicate rollover behavior. So if that's how mul works, I'm curious, how does imul work? Imul. Product twice the size of the input operand is stored at AX. Okay, so you're still storing there. With this form of the destination operand, the first operand is multiplied by the source operand. The second operand, the destination operand, is a general purpose register, and the source operand is an immediate value. A general purpose register or memory location, the immediate product, at twice the size of the input operand, is truncated and stored in the destination operand. So this just throws away upper bits. This form requires a destination operand and 2 source operands, the second and third. Here the first source operand, which can be a general purpose register or memory location, is multiplied by the second source operand, an immediate value. The intermediate product, twice the size of the first source operand, is truncated and stored in the destination. So these throw away the top bits to make it work. If you want to get the high bits of your multiply, then you need to use the 1 operand version. So in the situation I'm in, what I can get away with doing is just saying mul RDI, and that will give me what I want, right? And RDX must be a caller saved register. It would just make very little sense for it to not be, given that it's hard coded. Yeah. So I should be able to trample that. Here it is. Yep. Okay. So that means I should be able to do what's already in racks times this. What's in RDX will get thrown away. What's in REX gets divided by 2 by this shift right, and we return the result. That's not good. All right, so let's see if we can debug this. What we're going to try to do is use remedy for this. All right. Let's open up nope, sorry. I want to set the command that I'm trying to run. I'm not trying to run remedy. Mr. Forth build Euler.exe. Okay, can I step into it? Very good. Now if I step into this, ooh, okay, so it found our ASM file. Good, so debugging, there's nothing weird setting up debugging. That's good news. Now let's see if we can actually see this stuff. So that says RDI is some big number there. What about these other things? Do any of them look like the 5 I tried to pass? Maybe I just need to grab a registers window here. Can we do that? Registers, please. Yes, dock it right here. Do any of these contain RCX? So what's going on there? Why did it not follow what the ABI says? Maybe that ABI doesn't apply in the case of 64-bit and it's just 32-bit. Let me double check that I read it properly. Fourth argument register. Third argument register. Second, first argument register. Okay, so what do we make of this? Is it just disobeying the suggested argument layout? Is there a different argument layout? See, this is for x64, obviously. Also, why are the registers 8, 9, 10, 11, A, B, C, D, 1, 2. It feels like this can't be all the registers, right? Am I crazy? 1, 2, 3, 4, 5, 6, 7, 8. I guess there are 8 here and 8 there, and they just got them, like the RSP and RBP are down here. The original 6 besides those 2 are up here. Okay. So what do I make of this? Why is RCX5 instead of RSI? It must be a calling convention thing. I need to tell it what calling convention to use. Ah, that's another thing I should do. I should figure out if... So, Pew Pew Soldat in the chat is telling me that I need to... The ABI I'm looking at is for something called System V. So is that like the operating system I need to think about? Is it like Windows x64 ABI? Yeah, calling convention. Here we go. This makes sense. RCX, RDX, 8, 9, but this is not 5th and higher, 4th, 3rd, 2nd, leftmost. Okay. Why are they arranged this way? It's kind of a weird table, but okay. Integers, aggregate, M128 has a pointer, 8, 16, 32, or 64 bits. I don't know what it's talking about, but RCX is our parameter number 1. While we're at it, is there caller integers and caller callee save registers? So we probably want to throw this into the stuff I'm going to save here. floating points per blah 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 blah. Where is my call? Consider the registers REX, RCX, RDA. Volatile. When present, the upper portions are also volatile on ADX. So the registers are also volatile registers destroyed on function calls unless otherwise safety provable analysis, such as whole program optimization. The x64 API considers registers RBX, RBP, RDI, RSI, non-volatile. They must be saved and restored by a function that uses them. So these are different because RSI was a parameter before and it's not now, and also it's callie saved now, which is interesting. Okay. Okay, so my first parameter is going to come in on RCX, and then I'm going to return it to RAX. That's all I got to do. So all these things that I was saying, RDI, we want to do RCX now. Let's try that. And then, there we go. Okay, so we have a triangle number function. Let me take a quick note. Triangle number. Now what we want to do is let's compute our first sort of complicated expression thing here. We're not going to have any parameters, but we're trying to compute 3 times the triangle number of 1000 divided by 3 plus 5 times the triangle number. I'm going to shorten this to try. 1000 divided by 5 plus 15 times try of 1000 divided by 15. Drop in frames, let me check. I'm showing 0 drop frames on my side, so hopefully not. Maybe there's an internet issue or something though. Ooh. Not great. Let me know if it gets bad and I'll fuss with it. I'll keep an eye out on the chat. All right, so Euler 1 proc, Euler 1 NP. So how do we want to do this? We want to get the final results added up into RAX. So set something to 1000, divide by 3. Whenever we call a triangle number, the result will go into, that's got to be a subtract. Whenever we call triangle number, the result will go into RAX. So, well, one thing we could do, yeah. Interesting. So, yeah. Let's do this piece by piece here. Our goal is to call Euler 1. So step 1, let's just pick some random register and move 1000 into it. We could compute 1000 divided by 3 statically, like that's, there's no reason. Yeah, let's let's think for a second. Divide by a constant. Is there an easy way to do divide by a constant without having to do, if I divide by, yeah, I don't know any easy way to do divide by 3 with just shifts. Okay. Very interesting. Sine divide, Oh, we need to clear r dx to 0 to use this. That's where the modulus goes, right? You gotta clear that out every time. Okay, so what I'm gonna say is let me grab my calculator and do this, because if we were a compiler, that's how we would do it. We do not need to belabor the point too much. Okay, so there's 1000 RCX equals floor 1000 over 3. And then let's call triangle number. We're going to want to set, yeah, we got RCX the right thing, so RX will get the result. So if I did that right, it'll just give me the triangle number of 333, which probably looks something like that. So then, I need to grab a call or save register, RDX, to use that for my accumulator. So move into that from there. And what we'll do is just grab 1000 over 5. Call again, add that into RDX, and then one more time, put a sub here and a 15 here. 1000 divided by 15, 66. I'm skipping the multiplies. Okay. Gotta do that too. So let's do that. Suppose the easy way to do that is imul rax 3, right? Rax equals 3 times that much. RDX equals that. And we want to do call multiply rax equals that. Add RDX equals that plus that. RCX, RAX, multiply. Let's see, 15 times 15, and then RDX, all of that. Oops, wrong side, my bad. Minus 15 times 1,000 over 15. Okay. Why is it? Oh yeah, I'm using RDX to accumulate it all. I'm using RDX to accumulate it all, and then I have to move it back into RAX to return it. Right? That doesn't look great. So I might need to go through and check some of it, but I'm gonna do one more thing to sort it out first. So this is gonna be 3-part. This is gonna be 5-part. This is gonna be the 15-part. Yep, some bogus. Let's try and figure out what that's doing wrong. So RCX, can I get these in, I guess not. RCX, RAX, RDX. Okay. Will that, yeah, so that steps over the call instruction for me. That gives me something that looks good. 55611. Okay, I understand what's going on. I'm treating RDX like it's stable, but it's not. So after each one of these calls, I'm getting roasted by the call to triangle number, right? So I call triangle number, and then it does its work, and it does this mul, which roasts the RDX. Now, if I want to do this correctly, what I should really be doing is saying, I don't know how triangle number is going to get implemented in the future. So I have to use a call eSave register, or I have to use memory. And if either way, I have to use memory, it looks like, right? Like, isn't that true? Because I can't count on this to not trample my accumulator. So there's one way I could do it, which is I could not bother to accumulate into one register, but instead use separate registers. I just wouldn't be able to use RDX. I need to pick 3 caller save registers. I need to pick 3, actually, yeah, if I pick a call eSave register, then I have to save it in this function. If I pick a caller save register, then it's gonna possibly get trampled after each call. So either way, you're screwed, kind of, right? Like, there's no way to say, I want to, there's no way to say, I want to preserve something over this called a triangle number without having to use memory at my level to follow the ABI rules. So I think we'll just go ahead and do that. So let's see here. We need to do something like that, right? And then forget about this. Let's set that, right? So the memory on the stack right there is where we put the accumulator. Of course, we could solve this another way, which is to inline the triangle number computation, but I want to practice like dealing with function calls as part of this exercise, so that's what we'll do. Luckily, you can use memory locations in the middle of arithmetic like this. RSP, RSP, let me double check all this. That hasn't changed, that hasn't changed, that hasn't changed. Instead of RDX, we're now throwing something into RSP here. Like the first 8 bytes of the stack. Then we add that much into it, we subtract that much out of it, and move the result here. Okay. That looks like it could probably be correct. Let's try it. Project Euler. Check. Ah, it has signed me out. 1 second. Remember me, sign in. Okay, let's try this again. Copy. Check. No, not the correct answer. Okay. Let's think about what went wrong. I will just double checking that I'm typing it all in the way I think I am. All right, let's look in the debugger. Step in here. So 333. REX becomes 55611, and I want to see. This probably won't work. Yeah. So can I tell you that the thing at RSP is a 64-bit integer? What if I told you it's a uint 64? T? Okay, so you understand that one. Oh, what if I just did U64? Do you understand that? Yeah, you do. Okay. So U64 at the RSP, I go times 3. So there's the triangle number of 333. There's the triangle number of 333. I'll move that there. Okay, good. 200. Triangle number multiplied by 5. Add that to that. Triangle number. Multiply that by 15. Subtract that much. Put the result in RAX. Move RSP back. Yeah, that all looked like it happened the way I would have expected. So it might be just a typo somewhere or a mistake in some of the math somewhere. Let's see, how will I verify this? So we're going to use, we're going to use this side real quick. First things first, I'm going to just make sure a few things work the way I expect. We're going to assert the triangle number n plus 1 equals the triangle number n plus n plus 1. You know, quick loop here. Yeah. Okay, so triangle number is good. Just one other thing, triangle number of 1. Okay, yep, so if that's a 1 and the rest of these follow this constraint, then we're computing the triangle numbers correctly. So it must be the way we're putting this together. Either this formula was wrong or I didn't compute it properly. Let's test it like this. Okay. And then if I pop over here and run to here, what do we get in Y3, Y5, and Y15? Those look like the things I got before. So I think those are getting computed properly. And if I compute Y by doing Y3 plus Y5 plus minus Y15, okay, so my math must be wrong somehow. Let's double check that part. Where might I have made a mistake? So I'm adding in 3's. This is triangle number 1, 2, 3, 4, blah, 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 all the way up to 3, 3, 3. Let me double check that the prompt says 1,000. Yeah, below 1,000. Oh, did I accidentally do inclusive? This is like less than, or I am supposed to be doing less than 1,000 and it's computing less than or equal to 1,000 because this logic here works when 1,000, yeah, that was probably the mistake. Okay, so I think what happened here was I was saying, whoops. I was saying at this part right here that it's 1,000 divided by these numbers. But what happens in the case of 1,000 divided by 5? I get 1, 2, 3, 4, 5, there's a group. 6, 7, 8, 9, 10, there's a group, and so on. So here's like the first part of my triangle number, the second part, and this is going to go all the way up to 996, 997, 998, 999, 1,000, right? I'm going to divide that by 5, I'm going to get 200, and it's going to tell me that this is a complete group, but actually we're supposed to be doing 1,000 exclusive, so this isn't really an option, and this isn't really an option, so this is not a group. And I actually stop at 995 right here at 199. So what I need to do, this is wrong, right? This here is incorrect. That's what we need to try. Get rid of this part. So all these things that say 1,000 in the notes, those are mistakes. Those should say 999. And then I just got to recompute. Well, pretty sure this one just becomes 199. And the other ones should already be correct, I'm pretty sure. Yep, okay. So let's try that one. Let's try and put in the answer again. There we go. Alrighty, so we're about an hour and 40 minutes in here. I'd like to go for 3 to 4 hours on any one of these sessions, so we're going to try to go for another problem. Let's tidy up after that one though. So things we want to do, we can toss. We'll keep this around for now because it might be useful, but we'll toss this. We'll get ready to solve Euler 2. I'll toss Euler 1 soon. I'm just keeping it for reference in case I want to have something useful to copy paste to get me started on something. So let's see. Do we like the look of Euler 2? Even Fibonacci numbers. Each new term in the Fibonacci sequence is generated. Wait, before I get into this, now would be a good time for a break and a check if anyone in the chat would like to ask a question or discuss something. And I could use a break from talking the whole way through this, so. let's take this problem. Doesn't look like there's any chat stuff coming up. So this problem, each new term in the Fibonacci sequence is generated by adding the previous two terms. By starting with 1 and 2, the first 10 terms will be da 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 da. Okay, very clear. By considering the terms in the Fibonacci sequence whose values do not exceed 4 million, so values, not the 4 millionth one, but the ones whose values stay under 4 million, find the sum of the even value terms. Okay. So one easy way to do this, if we just wanted to get it done, would be to write a loop that visits all the Fibonacci numbers and accumulates the even ones. That wouldn't be too hard to do. But we're not going to get anything super reusable out of that, besides maybe the Fibonacci loop code, but then we'd have to copy paste that code and rewrite it. You know, if I sit down and write the code that does a Fibonacci loop, how I use the values I'm iterating there will be different all the time. So I wouldn't really be able to cleanly reuse that by turning it into a function. So I want to take a minute to think about what I could do to make this cleaner. The other thing is, I suspect, because how do I want to put this? The Fibonacci number, finding a sum of Fibonacci numbers is suspicious because Fibonacci numbers. Well, let's talk about this on the Milton. Let's see. You know what I should do? Come over here and zoom out a touch and go, here's problem 1. All right, and now I'm going to zoom out and come down here. Should have kept the same zoom level I had for writing problem number 1. So I'm going to come down here and go problem number 2. All right. So problem number 2. Let's talk about this. It gets really big as I zoom in. Is that really how big I wrote it before? Is it bigger now? Okay. Oh well. Problem number 2. Ready for this? We're gonna do a little discussion first. So the Fibonacci numbers are like, you know, 1, 1. They said start with 1 and 2. I'm gonna start with 1 and 1. 1, 1, 2, 3, 5. Let me try something here. These. They're not gonna help. 1, 1, 2, 3, 5, 8, 13. 1, 1, 2, 3, 5, 8, 13, 21. Let's go one step further. 34. Okay, so we're taking each pair and adding them to make the next one. So another way we could look at this is that these are sort of like already doing an accumulation thing. This here is a sum of these two things. This here is a sum of these two things, and so on. So to ask me to give you a sum of the Fibonacci numbers with some restriction sounds kind of strange, or not strange. It seems like there's tricks involved there because the numbers themselves, like if you ask me to give you this spot in the Fibonacci thing plus this spot in the Fibonacci thing, well, that's already kind of containing that by virtue of the fact that it's the sum of these two guys, which are both containing this and their sum and so on. You know what I mean? It's like the sums kind of interlock here a little bit. They build up on top of each other. So to add up the even numbers is going to have some interesting logic to it. So for one thing, I have here are all the even numbers highlighted. If I highlight the odd numbers separately, you'll notice that like in groups of 3, for each group of 3 I add, the odds and evens are equal, right? Right? Like this here is the sum of those, this here is the sum of those, this here is the sum of those. So if you give me an even Fibonacci number and ask me for the sum of all of the even Fibonacci numbers, in that from the beginning to that even number, right? Then that's the same as the sum of all the odd Fibonacci numbers from that beginning point to that stopping point, right? So let's make some notation so we can take some notes about this. So f of n, we'll do it this way, f of n equals f of n minus 1 plus f of n minus 2 whenever n is greater than or equal to 3. And then the first two are obviously 1s, right? So that's one thing we know about the Fibonacci numbers. Or that's a notation we'll use is f of n, and that's the law that they follow. Let's note this. Notation. Fibonacci law. Is that thing right there. Ugh, this handwriting. Let's try to do a little better. Fibonacci law. These things are right here. Okay. So, if that's what those are, then what we were saying with this even odd thing right here, the picture I drew, so this is my picture, right? I'm going to write that again, but using, let's do this, right? But using this F notation. So if I take the sum, actually, yeah, let's talk about this another way. So I could talk about this as the set of even and set of odds, or I could talk about the things that are multiples of 3. So f the sum from I equals 1 to sum n. Actually, let's use k, since we're already using n as the variable in the Fibonacci function. So if I take 1 to k here, and I look at the third Fibonacci values, pseudonym 73, usual notation f of 0 equals 0, f of 1 equals 1, and then even Fibonacci numbers are f3k. Yeah, that's how I'm doing it too. So like this is going to be f of 1. I guess I didn't start from 0, I started from 1, 1, just the way I usually think about it. But we end up with f of 3 is 2. So the even numbers are multiples of 3, right? And then that's equal to, if I take the sum over the same, whoops, I equals 1 to k. So if I take all of the third values, that's this part, that's the same thing as if I take all of the first plus all of the seconds out of each triplet, right? Okay, so that's interesting. And that's interesting to me because if I can find a way, if these two are equal, right? And then I say, all right, I want to, remember the problem we're trying to solve is to sum all the evens. So this right here is the thing I want, right? This is the sum of all the evens. So I guess I'm not going to take the time to fully prove it, but I can explain why that is. If you look at the Fibonacci numbers, their triplets always go odd, odd, even, odd, odd, even. And you could very easily see that that's, by just staring at it for a minute, just the way addition works. 2 odds gives you an even, and then you'll have an odd and an even twice in a row, and then you'll get 2 odds finally and get another even again. So you'll get this pattern over and over again. You could use modular arithmetic to figure it out too. It's going to be odd, odd, even forever, which means that these third ones are all of the even numbers. So if we're going to sum all the even numbers, that's the same thing as this. This right here is the sum of k even Fibonacci numbers. Right? So that's our goal. So if I can find a way to compute that quickly, that'll be cool. So I know that it's equal to this thing over here, right? And so it's like this thing here and this thing here are equal. So a way to compute either one of these, I'm kind of zoomed out by accident now. Let me zoom back in. So a way to compute either one of these would solve the problem. But I have another thing I could do, which is I could say if these things are equal, then the sum of all of the Fibonacci numbers given a multiple of 3, like if I'm using something that's multiplied by 3, if I'm taking triplets of Fibonacci numbers and I'm adding them all up, that's the same as taking all of the odds and all of the evens and adding them together, right? If I have odds on this side and odds on one side and evens on the other, then if I put them all on one side, that's the sum of all of them, right? So if I had something that was like the sum of I equals 1 to k, I'm just going to write this as all three of these, right? So f of 3i minus 2 plus f of 3i minus 1 plus f of 3i, right? So that right there is the sum of all 3k first Fibonacci numbers. And that's the same thing, since I know that this part, actually another way I could write this, yeah, okay. So that part there is the odd part, and I know that that odd part is the same thing as the even part. So what I can say is that that is equal to 2 of the thing I want. I equals 1 to k f 3i, right? So if I can compute the sum of all the Fibonacci numbers up to some multiple of 3 and divide by 2, then I'll have my answer. Okay, so how could I do that? Let's look at the Fibonacci numbers again, because that seems like something we should be able to do. So that's my next question. How can I get the sum of all the Fibonacci numbers up to some arbitrary k? All right. So how do I want to think about this? It's a little confusing because like f of n is, there's like this whole tree thing. I don't know that, oops, that should be minus 1. Minus 1 f of n minus 2. Yeah, I don't see any obvious pattern here, like the so this plus this, is it like 2 times f of n gives you f of n plus f of n minus 1 plus of fn minus 2. But then how do you get the rest of the... Yeah, that's not really a new idea. I think I'll try this experimentally. I'll just write down some sums real quick. So here we have our values of f. Here we have our sums. Right? 1. So the sum of all of them so far is 1. 1. Sum of all of them now is that plus that is 2. 2. The sum of all of them so far is the sum of these two things, this box and this box. So 4. 1, 1, 2, 1, 2, 3, 3, 4, 7, 2, 3, 5, 5, 7, 12, 3, 5, 8, 12, 8, 20, 5, 8, 13, 20, 13, 33. Let's get a couple more. 8, 13, 21, 33, 21, 54, 34, 88. Okay. Can I see anything here? Hint from pseudonym 73, try working out the sum of Fibonacci numbers of even index and odd index separately. At first it kind of looks like it's going to be related, but these don't work. 1 plus 2 is not 4. 2 plus 4 is 6. 4 plus 7 is 13. If I added those up, I'd get 3. If I added 4 plus 7 is 13. 7 plus 12 is 19. So this is like 13. 19. Wait a minute. Okay, yeah. Look, here's something. I don't know what your hint means yet. I might figure it out in a bit here, but one thing I have noticed staring at this is the sums here are related to the Fibonacci numbers directly, like this. Like this guy here connects to this one. This is this one. This is this one. This is this one, and so on. So my hypothesis, in mathematical lingo, my conjecture is that let's call this like the sum of f. I'll just call it the sigma function. My conjecture is that sigma of k equals f of k, what is that, plus 2 minus 1. So I think that's it. So I'm going to take a minute to make sure that that's right. Pseudonym 73 is saying yes, well done. So I have probably got the right idea, but I want to stare at this just a little bit longer to see why that's true. Maybe the evens and odd things will click if I do that. 4, 12. But if I can just prove this, then I'll have a formula that I might be able to work with, and then I can maybe ask you what the evens and odds parts are if I still haven't figured it out. So, how will I prove something like that? That's the kind of thing where it'd be fairly easy to prove by induction, because if you already know the sum up to a certain point, then the sum of the next thing will be pretty easy. So let's say we know it's true for all of these cases, right? So we have like, here's our proof. First we'll write note that the sum function of 1 equals 1, which equals, let's see, 2 minus 1, which equals f of 3 minus 1, right? Which we could also say is, just to overly highlight the whole point here, there we go. So this is like when k equals 1, and then if we say suppose that when k is less than n, we can assume that our idea works for k. Then, so whenever k is less than n, our idea works. So now we want to show that the idea then works for n, and we'll have the induction up and running. So we want to write an expression for sigma n. Sigma n is sigma n minus 1 plus f of n. We know that n minus 1 is less than k, so this is f of k plus 2 minus 1 plus f of n. Oh, whoops, not k. That's a mistake. Can I do f of n plus 2? Yeah, that makes more sense. So sigma n minus 1. Oh, that's not right. Okay, so it's not n plus 2 because we had a minus 1 there. So n minus 1 plus 2. So I see. So if k is my n minus 1, then k plus 2, let me just write a little bit more space here to plug it in step by step. So n minus 1 plus 2, my k is my n minus 1 is my k from up here, minus 1, so that part is written out faithfully now, and then f of n. Okay. And then that's obviously just f of n plus 1. Okay, so that makes sense, because that's going to give us something like this, and then by the Fibonacci law we can combine that into f of n plus 2, right? This plus this is this minus 1, so if I want to I can say like this is the induction hypothesis. This here is just basic simplification, and this here is the Fibonacci law. And so now we can conclude from all of this that if it's the case that k less than n implies the sigma function yada yada yada, then we get that our whole idea works for n as well. And so then by induction, this formula works. Cool. Okay. So I guess I can see why even an odd index would be relevant, since this +2 is showing up, which means that there's like this one and this one here. So like the sum of the wait, hold on. Sum of these 1, 3, 8. Oh, I see what you were talking about now. It's not these. These aren't the thing you were pointing out. It's this. If I took 1 plus 2, I would get 3. If I took 1 plus 2 plus 5, I would get 8. 1 plus 2 plus 5 plus 13. Yeah. Yeah, so this guy here is always the sum of all of these. Oh, that's fascinating. I don't entirely have that clear in my head why that's true, but that makes a lot of sense. So that then tells us like that this here is 3 plus 5, and then this here breaks down into the sum of this and this again. Because this guy is, yeah. That's cool. Okay, so I think I have what I need. I know how to compute this. I compute the sum of all of the Fibonacci numbers and divide by 2. And I know how to compute the sum of all the Fibonacci numbers up to a certain point. I go 2 past that point and subtract 1. Okay. Okay. Let me take a note here. I'll zoom out. So far what I have is that my goal is the sum I equals 1 to k of f of 3I, which is equal to the sum, I'll say I equals 1 to 3k f of I. I'm kind of skipping the step of like the rearrangement there, but it's fairly clear, all over 2. I don't want to write it that way. Let me tighten this up. Equals 1/2 of the sum of all the Fibonacci numbers up to 3k. F of I which I have now discovered is 1/2 of f of 3k plus 2 minus 1. So what's left to do is I need to, how do I compute f of k quickly, right? I could just run the whole Fibonacci simulation, if you will, like the linear scan all the way up to k, and then however big the thing I put in is, that's how long it takes. But I wonder if there's a faster method. And 2, for arbitrary, why don't I back this up for a minute? For arbitrary K, to how do I compute K? I mean, one easy way to do this would be to say, forget doing this fast, scan along the Fibonacci numbers until we find one that's over 4 billion, or 4 million, whatever the 4 billion, over 4 million, go 2 more, subtract 1, divide by 2, you should have an answer, right? Well, that's not quite right. I have to make sure I'm on the third. I have to make sure I'm in the right spot of the 3 there. So it's not just go to one that's over 4 million. Go until you find one that's over 4 million. Then get yourself to a point where your index is at is 2 modulo 3, and then you're done. So you might be done right away. You might need to do 1 or 2 more. Yeah, you gotta like fiddle with that. I might be accidentally including the 4 million, which I think I'm not supposed to do. Let me read this again. Not exceed. Yeah, so I have to make sure that I'm not doing it in a way. Yeah, there's like an off by 1 trick I have to work out there at some point. But I wonder if there's a way to figure out what K is. Without having to just check them all. Because if I end up having to check all of them anyways, I might as well do it the linear way. Let me think. What do I know how to do here? Fibonacci number. Find K. How do I find K such that f of K is so how do I find the largest K so that f of K is under some maximum, some capping value? Yeah. If there was like a log function, what's like the fib log, right? That takes in, what's the fib log? It takes in a value x. So that you round it down, that value is less than or equal to x, and that's less than or equal to that. You round up the fib log, right? Something like this. It's a little bit not helpful, kind of notation heavy, but the idea is like, can I find a function which undoes the action of the Fibonacci function, right? Fibonacci takes a natural number and blows it up to some sort of large like curve. Can I find an inverse? And that's going to give me a problem, which is that when I put 4 million in, it won't necessarily be a Fibonacci number. But I want it to give me something as close to, like I want it to be able to give me the upper and lower values around that Fibonacci number if it's not a Fibonacci number, and just give me the correct index if it is the Fibonacci number itself. Right, so how do I invert the Fibonacci function, essentially, is the question. I call it log because I was thinking of how exponentials are inverted by logs, so it's just the inverse of the Fibonacci. Well, I might be able to compute that by hand because I know for a fact that there's some way to compute the Fibonacci number directly. Like this part I know is possible to do analytically, but I don't remember how that's done off the top of my head. I might have to do a little math digging here. Fibonacci number golden ratio is something like this. I get like Wikipedia Fibonacci Fibonacci numbers closed form expression. Yeah, here we go. I remember I've seen this before, and it's kind of cool how it's derived, but it kind of takes a little while to go through it. There's the formula. Right, these follow that Fibonacci law thing. Ah, right, that's how it works. Interesting. Because linear combinations of this. Yep. Okay. I think we can do it this way. I'm gonna skip the deriving it because I remember how it works. It's just, I mean, it's all here. There's no point in me doing it now that I'm getting help to find it anyway. But it's kind of neat. So I was just going down the rabbit hole of remembering how it works. It's like if you take the golden ratio, the connection between the Fibonacci numbers and the golden ratio is that the golden ratio itself, when you like raise it to an arbitrary power, because the golden ratio has this property, x squared equals x plus 1, and then if you multiply by x, you get like arbitrary powers over here, and this is the same thing as the Fibonacci law, right? X to the n is x to the n minus 1 plus x to the n minus 2. So the multiplying by x, the whole equation shows you that each multiplication by x is like iterating the Fibonacci sequence, essentially. And then there are two numbers that satisfy that law, and you take an arbitrary linear combination of those so that when you add them together, you get this. You have this going on. Yeah, it's pretty neat, but I don't want to get my head all the way around it right now. So I'm just going to take this part here and see if I can use that to solve for K. So let's see if I can write that down first. Put that side by side with that. We lost it. All right. So Wikipedia says is equal to phi to the n. I can't remember which of these is, but that one's phi, right? Minus this guy to the n over root 5. Pseudonym 70. Okay, pseudonym 73 has just had a few things I should check out. He started by saying that you can approximate this by dropping this term. So let's write down what those are. So this here is there it is, 1 plus root 5 over 2, and this one here is 1 minus root 5 over 2. And if you look here, this is smaller than, like this is raising this to higher and higher powers, it's going to go to 0 because it's less than, it's between -1 and 1. This one here is going to grow. So this is going to, as we get closer to 4 million, it's going to be dominated by this part. So what we'll say is f of n is approximately equal to, and that's exact, that first formula we have, but we don't want to complicate things. So that is a good approximation. So if we want to figure out what value to make f of n about 4 million, we want to solve 4 million equals, man, oh man, I do not know how to write with the tablet or how to use Greek letters. It's a nasty combination. Okay, we want to solve that. So we get n equals 4 million root 5 over that guy. And plug that into a calculator. $4 million. Double check that I'm doing this problem right. Not exceed 4 million. Okay, keep doubting whether I'm doing the right amount. Divided by, I've got to type in the expression for phi here. 1 plus the square root of 5 divided by 2. Okay. That's weird. That's... Oh, duh. Nope. Don't do so much in your head at once. Okay. So this should be log base phi of 4 million root 5. Okay. That phi still looks like crap. Let's make it a little bit tidier like that. Okay. So let me see if I can do that. I need to put 1 plus root 5 divided by 2. Let's save that into a calculator variable. And 4 million. I'm doing this on a physical calculator because it's just way faster than using the one on the computer. 4 million times 5. Put that into another variable. Okay, so 4 million times 5, we want the log of that using base phi, but that's not a button my calculator has, so I'll do log of this divided by log of that. Okay, so this suggests that it's around 33. Exactly 33.2 and some change, right? But we just want to care about the 33 part anyways. So in order to check that, all we'll have to do is be able to throw in 34 into our Fibonacci function later and see what result we get. We think 33 is the right amount. Okay, so there's our answer for part 2. Now let's see if we can get an answer for part 1. How do I compute f of k quickly? So I mean, one way to do it would be to just do the one way to do it would just be to do this, the closed formula. I'm a little concerned. I'd like to come up with a way to do Fibonacci numbers because they might come up again later in Project Euler problems. And if it has to use irrationals like that, I'd like it to be precise, and I don't know, like 4 million is not getting very close to the high range of precision yet, but if they want something like up to the value of 1 billion, then I feel like, you know, I guess you could use doubles. Seems like there's got to be a good way to do this. So like, let me just play with this for a minute. It feels like the kind of thing where you should be able to skip ahead by. We know a bunch of tricks now, right? Like we know that if you add up every other one, that's another way of computing a value. And the same way that I said at the beginning, they're all kind of these sums are all interlocked. It seems like there's going to be a trick. So like usually what you do is you have you start with like a equals 1. Let's just write down the code. I think this would be a good place to start. B equals 1. And you go loop C equals A plus B. And you're like, there's one of our values. And then A equals B, B equals C. I guess another way I could write this that would simplify this is if I said like, forget C, we'll just say A prime equals B, B prime equals A plus B. So the B shifts into the A. So it's like 1, 1, here's your A, here's your B, and then you get 2, and here's your new B, here's your new A. Yeah, so A is my low value, B is my high value, right? 3, here's my A, here's my B, and so on this way, right? So So if I wanted to do two steps at once, what would that look like? Well, that would be like going, what's A prime prime B prime prime? So this is like basic algorithm. Prime prime B prime prime. Okay, so A prime prime is just B prime, which is A plus B. B prime prime equals A prime plus B prime, which is B. A prime is B. B prime is A plus B, which is A plus 2B. A, B. Wait. What if we just keep this going for a minute? Let's do another round of this. A prime prime prime. Does a pattern come up or something? B prime prime equals. So B prime prime, we already know what that equals. A plus 2B B prime 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 equals A prime prime plus B prime prime, which equals A prime prime is A plus B. B prime prime is A plus 2B, which equals 2A plus 3B. I want to like highlight these. AB, A plus 2B, A plus 2B, 2A plus 3B. That seems suspiciously regular. So for A, B, A2B, A2B, 2A, 3B. Oh, it's just going to accumulate a bunch of Fibonacci numbers, isn't it? Let's look. I think it will. Which kind of is frustrating because that means that maybe I don't have anything. 2A plus 3B. B prime 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 equals A prime 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 plus B prime prime prime. A prime 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 is A plus 2B. B prime 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 is 2A plus 3B. 3A, yeah, look at that. So whatever A and B you start with, the follow-ons there are just like the fourth iteration is the 1, 2, 3, 4 is the fifth and fourth Fibonacci numbers combined like that. So to skip ahead, you still have to know the result anyways. At least to skip ahead using this method. From there. So this, wait a minute. So this is, so this is like a pair of numbers here. There's something, so I'm thinking about, like, if I took a pair and put it into a function, or I don't know if that's the right way to think about it, but like if I think about the concept of a pair of numbers, A and B are acting as a pair. They're like, here's one of my pairs, here's one of my pairs, here's one of my pairs, and so on. And this here is also a pair, right? So what is, let's write this down real quick. This is A, B, A prime, B prime, A prime prime, B prime prime, A prime prime prime, B prime prime prime. So I could replace this 3 and this 5. How can that be? Oh. A prime prime prime, B prime 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 are 3 and 5 because A and B are both 1. A and B are both 1. A prime prime prime, B prime prime prime. So like what I have here, another way I could write the same thing I've got is I could write it as A prime 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 equals, so that's 2. Now what is 2? 2 is A prime prime A plus 3. What is 3? That's, I could say that's B prime prime. I could also say that's A prime prime prime. B. And I could say that this B prime 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 prime, right. So the B with 4 primes, that's A prime 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 A plus A prime 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 B. So like the second, third, and fourth numbers all go into computing this one. So B prime prime, like this is the same thing as this. Yeah, I'm just okay, so one thing that's kind of neat though, hold on. So you could use any of these formulas to step by multiple at a time, right? So if A and B are both 1, this is just like a fixed formula for getting to from like the first pair to the, like, what is it, second, third, fourth, fifth pair. So it skips you ahead like 1, 2, 3, 4 pairs. If you plug in A and B to this formula, 2, 3, 3, 5, then you skip ahead. If I plugged those in again, if I put A prime prime, 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 b prime, 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 prime into these formulas where I currently have a and b, doesn't that skip it ahead again? Wouldn't that be the same thing as if you had started with a different a and b? Like, yeah, because you would just say start with a higher value here and then you apply this 5 times. Yeah, so this does let you like apply multiple at once. Okay. So like this is like right. So like if I go like 2, 3, 3, 5 and make a matrix out of this, and then I put in my A, B here. Did I do that right? 2A, 3B. Yeah. Then I could say like A prime, 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 B prime, 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 prime is a new vector you get by that multiplication, right? And then I could say like, so this gives you 4 steps ahead. Then A, we'll switch to using these 8, B 8 would be the same thing as this again. With these, right? So I could at least skip ahead. I could skip ahead by however much I want. But I have to get to the matrix I want to skip ahead by somehow. But every time I skip ahead, I find a new matrix too, because these are just okay, hold on. This is interesting. So if this here is a Fibonacci number, so this is like, okay, so we have some fn minus 2, fn minus 1. Oops. We have some matrix that looks like this, right? Now I have to figure out those 3 values of the Fibonacci sequence. But if I do that, then I can take any, so like if this was 0, 1, and 2, you'd have 0, 1, 1, 1. You'd put in the 1, 1 here, and you'd get out a pair that's like 1, 2. So that gives you 1 step forward. So whatever value, let me write this a different way. Just be sneaky, I'm going to write it like this. So if n equals 1, then when I put something into this, I step it forward by 1. Right? So it becomes, so if I put in whatever pair I put in here is going to be like some f of k minus 1 f of k. Then I'm going to get over here, the point is f of k, that n there, right? So f of k plus n minus 1, f of k plus n, right? I step forward by n whenever I do this. And then I can use those to build another one that steps forward by k plus n's. So if n starts off at 1 and k starts off at 1, then I get 2. And then if I take that and I apply it again, I get 4. Right, if I apply that to itself. So if I make a new matrix where n is 2 and then I apply that to the one where k is 2, I get 4. And so I can actually like exponentially move through the indexes rather than linearly. Oh, this is so this is the what do they call this? The squaring algorithm? I forget what it's called. It's like okay. Okay. Here we go. I don't know what it's called, but there's an algorithm that we can use here to make this go fast. So what we'll do is we'll start with the matrix 0, 1, 1, 1, right? And then we say we want to, this is the Fibonacci matrix. So this is, we'll call this right, so that's, whenever we apply that, we step one step forward in the Fibonacci sequence, and the idea will be that like f of n minus 1, f of n equals this guy right here, f of n minus 2, f of n minus 1, right? So yeah, if we do the math out here, this ends up being f of n minus 1 times 1. This ends up being f of n minus 2 plus f of n minus 1. Fibonacci log gives us that should be f of n, so that's the idea. And then, if applying it once is like this, then if you want to step more than once, you raise this to a power. So like, if I step 10 times, then it's going to be like, so let me just say this. So k steps is equivalent to applying 0, 1, 1, 1 to the power of k, right? So if you want to step once, k equals 1. If you want to step 10 times, it's just 10 of those in a row, right? And so now the question is, how can we quickly compute a power of a 2 by 2 matrix that looks like this? And the way we can do it is using an algorithm where you square over and over again, right? So you can take this and you can take a 2 by 2 and square it pretty easily. And you keep on squaring it, and then you end up with a table that's like, I don't remember what this thing is called. We're going to call it the squaring algorithm. Okay. So the way this algorithm works is you go, here we're going to have our powers, k, and here we're going to have our values, v. Our v's could be whatever we are squaring. So in this case, it's a 2 by 2 matrix. And we go like 1, and then 0, 1, 1, 1. And we go square that. Now our power is 2. And so then we get that squared. Well, I know that these are just Fibonacci numbers, so I'll use that to fill it in. 1, 1, 1, 2. Okay. Now if I square that, my power doubles. So I go from a power of 2 to a power of 4. And then I say, okay, what is this matrix squared? So that's going to be, top left is 1 plus 1. Top right, 1 plus 2, 1 plus 2, 1 plus 4. Yeah, makes sense. 8, right? You get the idea? I guess another way I could write this is like v to the 1, v to the 2, v to the 4, v to the 8. Then you keep doing that until you get to the point where you've got all the powers you need. And you're trying to find the power of your thing to the power of k. So like, once you have all of these, you can assemble k, because these are powers of 2 here, right? 1, 2, 4, 8. We're doubling the power, and we're squaring the actual thing to accomplish that. because basically multiplying something by itself is easy, but raising something to an arbitrary power is hard, right? So like repeated multiplication easier than powers, right? That's the idea. So once we've done some repeated multiplication, we have this table that'll tell us how each of the bits corresponds to a particular value of v. And so like we're trying to get to, if we have k, well, basically I'll say it this way. So then the idea is we have v to the k for an arbitrary k is just v to the, how do I want to do this? I should do this. Let's make this p. Okay, v to the k is equal to like v to the p1, v to the p2, v to the p3, where we selected these things here based on what bits are set in k, right? So in other words, like this corresponds to k equals p1 plus p2 plus p3. Hopefully that makes sense. So we have some way to break k down into a bunch of numbers that we can add together. And by using the fact that v to the k, it can be broken down into a bunch of these multiplies. Once we do multiplies to build the table, then we do repeated multiplications at the end to combine things from the table that give us something v to the k, right? That's the idea. And then we can actually do this without building a table. We just say, like, as we're going, if we hit a bit that we want to keep, we throw it into an accumulator by multiplying it in, right? So like we can do this algorithm without building a literal table, but like conceptually, I think that's an easy way to think about it. You build this table by repeatedly squaring the same object, and then you break down your power into a bunch of ones and zeros, and you say wherever I see a 1, I multiply that object into the final product. Okay, so if I think this will work. So let's go and try to write something that'll give us a Fibonacci number using a technique like this. So we don't actually need 2 by 2 multiplication. Like 2 by 2 matrix multiplication would be a little bit overkill. We only need 3 numbers. So let me think, let's spend one more second over here. So let me work out, let me work out what we're actually going to do. So what we're actually going to do is something like, we have 3 numbers that start off like this, 0, 1, 1. We'll call this a Fibonacci step. Now, we want to be able to do 2 things with a Fibonacci step. One, we want to be able to say, combine 2 Fibonacci steps. So like this right here is the Fibonacci step at f equals 0, f1, f2, right? So every Fibonacci step will have that form. Actually, let me write this a little bit differently. So a Fibonacci step will be a triplet of numbers, f n minus 2, f n minus 1, f of n, and an example of this would be 0, 1, 1 as a triplet, right? Where n equals 2 in this case. Okay. So if that's example. Okay, so if that's a Fibonacci step, then what I want to be able to do is let me give this a little bit more care here. Fibonacci stepper. And I'm going to give it the short name FS for the type, right? Need type name. I'll do one of those guys. Okay. So if that's my Fibonacci stepper thing, then in one way it only takes one integer to define this, but I'm actually going to think about them as having 3 integers because that's how I'm going to program them to get performance out of it, because then all the computations will be cheap. But they're actually like just, it's basically just an index into the Fibonacci sequence represented as a triplet in data, right? Man, my penmanship makes this really rough. Okay. So what I need is a multiply that looks like this. It takes in a Fibonacci stepper and another Fibonacci stepper, and it outputs a Fibonacci stepper. And it should be the case that the multiply operation it should be the case that the multiply operation, when I do it on 2 triplets here, fn minus 2, fn minus 1, fn, and then fk minus 2, fk minus 1, fk. There's my triplet. That should give me the stepper that adds n and k together. So fn plus k minus 2, fn plus k minus 1, fn plus k. Okay. Okay, so the way we can do that is just probably by applying a couple. We could either look at the way matrix multiplication works and do a little bit of that, or just see if the Fibonacci rules will get us there. I guess we can't use Fibonacci rules because we don't know how to get big an n and k will get. So let's look at the matrix version. So that's like saying I want to multiply these two things. Fn minus 2, fn minus 1, fn minus 1, fn times fk minus 2, fk minus 1, fk minus 1, fk. So you get a new matrix that looks like this. It's gonna You're going to want to zoom out for it. It's going to kind of have a lot of writing in it. Fn minus 2 times f of k minus 2, that one and that one. You know what, I should have picked a simpler notation. Yeah, let me see if I can just undo a bunch of this. I can do this with simpler notation. Okay. I will re-put in this dividing line here. And then we're going to say A1, A2, A3 multiplied by B1. I guess the other reason I had it in the bigger notation before was so that I could define the rules of the multiply. Yeah. Okay. I gotta stop doing that. Let's redo the line, erase some of this, and I'm going to rewrite this part. I need to establish a little bit more notation that I can use. So the Fibonacci stepper Fs of n is the triplet Fn minus 2, Fn minus 1, Fn. So then if I have Fs n multiplied by Fs k, that should be Fs n plus k. So now I've defined the thing, I've left in my notes the thing I'm trying to actually construct, which is the multiply for two of these triplets that has this property. And the way I think I can do that is by taking a look at these two matrices, right? So I'm going to say F, we'll just call it N1, N2, N2, N3 times K1, K2, K2, K3, and that's going to give me N1, K1 plus N2, K2. Over here, I get N1, K2 plus N2, K3. Down here, I get the same thing. And then right here, I get N2, K2, N3, and K3. All right. All right. So that's not so bad. The new tuple, or triple, I mean, is just like this. I'll call it. I'm using n and k, so I'll switch to R1. Result 1 equals N1 K1 plus N2 K2. R2 equals N1 K2 plus N2 K3. R3 equals N2 K2 plus N3 K3. Okay. that is something we can compute with a very simple algorithm to multiply two of these things together. But we could do even better if we know we're squaring it, right? So that's the definition for a general multiply. But we only need square. Oops. Oh, that's not true. We do need general multiply for the final step, but we can go faster for squaring. And that's because we can go R1 equals N1 squared plus N2 squared. R2 equals N1 N2 plus N2 N3. R3 equals N2 squared plus N3 squared. Okay, so we're going to go write both of those functions just to get us started. Okay. So let's see. Fibonacci stepper mul proc. Fibonacci stepper mul NP. Alrighty, so our first parameter is RCX. We'll call this dest. And let's see, what was our second parameter? RDX. Source. And now we want to do, okay, so how do we do mul? We have that written down up here. N1, N2, N3, N1. So there's 1, 2, 3, 4, 5 different intermediates that need to get computed. We're done. N1, N2. This spot here is N1, K2, N2, K3. N2, wait a minute, this one's different. It's my understanding that these matrices always we're going to show like this. I think they have to. If I take two matrices that have this sort of symmetry thing, don't they always keep that symmetry? So how is it that here, N2K1, N3K2 must just be the same as this other pair, N1K2. I don't see how that is though. N1K2, N2K3. and 2k1 and 3k2. It just doesn't look like it would have to be different, does it? Or it have to be the same in the general case. This is a little confusing. I need to think about this for a minute. Is that the case that in the general if these are not equal always, then what are they? I thought these would always be Fibonacci numbers based on what I was looking at earlier. Let me zoom out and think about this a minute. Yeah, 2, 3, 3, 5 was what came out of this part. 1, 2, 2, 3. Yeah, it seems like every time you apply okay, I just need to take some notes real quick. We can erase them when they're done, but I'm a little confused about some things. So suppose I have a couple of matrices. I'll call this one X, Y, Y, Z, and A, B, B, C. Don't you get X, A, Y, B, X, B, Y, C, Y, A, Z, B, Y, B, Z, C, right? So it seems like in general, you can't guarantee that these will be equal. So there must be something else that guarantees it in this case, I think. It just doesn't seem like there's any guarantee that this is symmetric. But what about the case where I have specifically zero, one, 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 like that? Because then maybe it'll be different. X is gone. Y. Wait, X, Y, 0, 1. So Y. X, Y, 1, 1. X plus Y. Ah, yep, there it is. This is Z, and this is Y plus Z. Yeah, so in this case, they'll always turn out to be that way because we're building out of this particular matrix, and every time we apply that particular matrix again and again and again, we keep getting equality here, and that's not surprising. This is the slot that remembers like the nth Fibonacci number, and this is the slot that remembers the sum of the previous two Fibonacci numbers before that, so they will be equal. Yeah. Okay, good. So that means that I didn't screw this up. It is true that I can compute this one of either of those two ways. It seems a little weird to me. The reason I went into that whole thought process, I was thinking like matrix multiplication. It's weird to me that I was expecting order to not matter because the way these are combined, it should be commutative. I'm combining two indexes to skip ahead. I'm trying to make a thing which takes two Fibonacci numbers and combines them in such a way that it's as if I added the indexes of the Fibonacci numbers and got a new Fibonacci number with that index, right? So I'm like, combine two Fibonacci numbers to get a new Fibonacci number that's equivalent to the index, the sum of the index, the number with the same indexes from before, but summed together, right? So I'm trying to make that thing. And so that means it should be commutative. It should be the case that I can rearrange this plus sign here and therefore flip around this and get the same thing. And yet here it was like, wait, N1, K2, N2, K3 is not symmetric. So if I switched N and K around, this would be different. And it's true, you'd get a different formula, but you'd get the same result. Okay, so that spookiness set aside. So what I'm trying to think through now is like, what's the order I want to do these things in to like make it as tidy as possible. I think I want to use up N1, because N1 is going to be like the one that gets replaced by R. So once I write to R1, I won't have N1 anymore. So first I will use up N1, because there's only two spots where I need to use N1. And then I'll square this, then I can write to that. Then I'll do this, and I can write to that. And finally, I can do this and write to that, right? So here we go. Step one. We're going to compute N1 times K1. So we want to put in don't care too much, put into racks whatever's at RCX, and then we'll IML whatever's in racks with whatever's in RDX, right? So we read out of this one, we read out of this one, we multiply them together and put them into the first register. So there we have N1 times K1. Now let's get N1 times K2. I need to check the caller save registers. So racks I can use, RCX and RDX I can't use because those are my parameters. So the only other caller save register I have are these guys here. So I want to move into R8. RCX. I want to IML into R8. RDX plus 8. All right, and then I'll return. Let me see if that compiles so far. It's looking for Euler too. Let me just throw that in there real quick. Okay. So we grab N1 times K1, N1 times K2. Not here. N1 K1, N1 K2. Now we need N2 K2. That's like this again. We'll use R9, grab those. And then we can throw We can throw out N1 now, right? We're done with N1. So we can move into RCX. What we have in racks. And then we can mull what we have in RCX by what we have in R9. So here we get oh, that was confusing. I picked R for that, but I'm going to switch to M for my result. The multiply, or maybe P for the product. So we're going to say P1, because I don't want to use R numbers here since I'm using those for register numbers, and I have to use those as the names of the registers. So P1, which is the first slot in the product, is going to be the sum of these things, N1, K1. So who's N1, K1? That's racks K1 plus N2 times K2, which is racks plus R9, right? So there we go. We've now got R9 free, and we've got RCX, or RAX for, right, RAX free. Both of those are free. No. R9's not free. We want to use that again. So let's multiply these and romp over that one next, right? We can throw away RAX though. So RAX equals N3 times K3. Let's move into RAX, RCX plus 16. Move into multiply into that RDX plus 16. So now RAX has that much, and then P3 equals N2 times K2 plus N3 times K3. So we move into RCX plus 16. R9 plus RAX. Okay. R9, and then we add into RCX plus 16 RAX. Okay. So this one is used twice and done. This one is used, and N1 has been romped over, but N2 is still free. So we can use N1 times K2 we still have sitting around. N1 times K2 is in R8 from earlier. And then we can multiply these together. We can use any of our registers now and then add them together into that spot. Okay. So this is going to be RAX equals N2 times K3 N2 is RCX plus 8 This is RDX plus 16. And then finally, I gotta figure out some way to make the boundaries stand out more. I think the best way will be to do this. If that's allowed. Hopefully that's allowed. chat out there. Okay. Should definitely wrap up soon. We're 3.5 hours in, and I can feel myself being a little tired and sluggish here. But we are almost done. I think we can finish the Fibonacci stuff if I keep my head on task for a little bit longer. N1, K1, right? We got N2, K2. So P1 is set, P3 is set. We're trying to set P2. P2 is supposed to be N1 times K2 plus N2 times K3. N1 times K2 went into R8. N2 times K3 went into RAX. So move into RCX plus 8, R8. Add into that slot RAX. Okay. Okay, if this works, I should be able to call Fibonacci stepper mul on stepper 1, stepper 2. That should modify stepper 1. Why don't we this around? This should modify stepper 1 to be one more than these. So 5, 8, 13. Do, 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 do. 5, 8, 13. Cool. All right, so I think the mul is working. Let's just do one other trick here. Does this give me a Fibonacci triplet from much later on? 55, 89, 1. Yeah, this looks like it's working. Okay, cool. So that's how we multiply any two arbitrary steppers, but let's figure out how we square a stepper. So squaring a stepper will look like this, and Fibonacci stepper square. RCX is best. Fibonacci stepper square proc Fibonacci stepper square. And proc, okay. So the way we square a Fibonacci stepper is similar but simpler. 1, 2, 3, 4, 5 values still. We can romp. So the hardest one to romp over is R2, but actually, as soon as you romp any of them, you have a problem. No. Okay, so we first compute the middle one because we can save n squared in a register and then put this value into there, right? Okay. And then we don't need either of these things, and we can use n2 twice. That'll be the way to do it. So let's get n1, n2, and n2, n3. Oops. n1 times n2. Let's see, racks equals n1 times n2. Then move into racks the value you find at RCX. Then we're going to imul into racks the value you find at RCX plus 8. We have another register available that we didn't used to have because this is there's no RDX because we're not using two parameters now. So we can move into RDX. Actually, why don't we do these? Let's just get like even fancier here. N2, N3. I don't know how much this matters, but it seems to me like it might be cool if you don't emit reads if you don't need to, but it might also be like, totally handled by the front end of the processor, which I don't actually know about that stuff. I know that if it's going to hit cache, it's slower to do the memory read, but if it's like something it knows hasn't changed and so it can use one of its, like if the processor can put it on something closer than the cache, like in just a hidden register in the parser, yeah, I don't know. I don't know if it's capable of that kind of thing. But that's an interesting question. So for now, we're going to say load N2 because we're going to use it twice. Load it out of memory first and then copy that into another register. Multiply N1 on that one, multiply N3 on that one. And now what we've done is avoided doing an extra memory read for this one, if that matters. No idea if it does or not, but it could, based on as much as I know. And then we're going to save n2 squared. So we're going to put R8 equals n2 times n2. So R8, oh man, we could do that one up here too. R8 here we romp over RAX with a multiply, here RDX with a multiply, and then R8 gets imul R8, R8. You just square it like that. Okay. So now we're going to say P2 equals N1 times N2 plus N2 times N3. Oh, wait a minute. What if you wrote this like this? Is that better? I mean, that's one less entire arithmetic operation. I probably should have looked for that. So I don't think up here, yeah, here there was nothing. Here we can do better. Okay. Let's just take a step back. Yeah, so let's erase this box for a moment and put in the observation that this is the same thing as N2 times N1 plus N3. So first we want to get N1 plus N3. move into RAX, the thing from the beginning of the stepper and the end of the stepper gets added onto that. Then we grab, now we're going to do RDX equals N2 times N1 plus N3. And at the same time, we're going to do R8 equals N2 times N2. So we're going to move into RDX, the thing you find at RCX plus 8. We're going to move into R8, a copy of that. We're going to multiply RDX, which has already got an N2 in it, with the stuff from, no, we can do even better. We're going to make RAX this and RDX this. So we move into RDX, the stuff from here, we multiply RAX, which already has an N2 in it, that we can now throw away. No, we don't need to throw away. The N1 plus N2, the N1 plus N3 we can throw away. So RAX has the N1 plus N3 in it. We grab an N2, and then we multiply that into the RAX, throwing away the N1 plus N3 and keeping the N2 times N1 plus N3. And then we take the RDX and we square it, right? So now we have computed the multiplication. We want to store it. So we don't need any more N2s. Is that true? Yeah, we don't need any more N2s because we've already got in a register the N2 squared that we need. So P2 can become N2 times N1 plus N3, which is just RAX. Move into RCX plus 8, RAX, easy enough. And then we can make RAX equal to N1 times N1. Multiply that by itself. You can add that to RDX. Save that into P1. We'll just do this all in one go. That seems clear enough to me. And then same thing with P3. N3 plus N2 times N2. Right, so RAX grabs this guy now, square it, add in the N2 squared, and store it back out. Okay. Good enough. So let's see if that looks good. 1, 1, 2. Let's just run the step a few times and see what happens. Ah, that's not right. No, yeah, that's right. It's squaring. So 1, 1, 2. Let's throw in. Gotta remember, it's not stepping up by 1, it's squaring. So that means every time it's picking a Fibonacci triplet like deeper in the sequence. You can see we got pretty close to 4 million after just a few steps. 1, 2, 3, 4, 5, 6 steps, and we're there. Okay. it's applying. So if this step, this is essentially 2. This is 0, 1, 2. This is 1, 2, and 3. This is 3, 4, and 5. This is 7, 8, and 9. So yeah, this one in the middle is doubling. So this must be the 16th, and this must be the 32nd Fibonacci number. So it's the middle one that gives us, this is Fibonacci number 1, 2, 4, 8, 16, and 32. Cool. All right, so we got our building blocks there. So now I want to compute the nth Fibonacci number on demand. What's kind of interesting about this is a faster way to get to a Fibonacci number on demand, but if you wanted to do something that involves looking at every Fibonacci number, you would still be faster to do the loop, right? The loop would be way faster if you're going to hit all of them. But if you want to get just the 100th Fibonacci number and you don't care about anything before that, this is faster, right? If you didn't already, basically if you already know the 99th Fibonacci number, this is a huge waste of time. But if you want to know the 100th and you haven't figured out the 99th Fibonacci number yet, then this is the way to do it. That's kind of the idea. So what I want to see is RCX is n. This time we have to return something, and that's got to be the nth Fibonacci number. So the way we compute the nth Fibonacci number using this technique is the squaring algorithm. So the exact way it works is a little bit detailed. We need a loop. So let me sketch out the like code. I'm gonna pseudocode it real quick, just because it will be harder to write the assembly if I don't even know how it would work in the way I normally think about code, right? So here's the algorithm I have in mind. Well, let's put this over here. Here's the pseudocode we want. Okay. How does that keep happening? So here's the pseudocode I want. We're going to have an n come in. And I want something like so let s equal 0, 1, 1. Well, I guess first things first, I want to throw in just that if n equals if n equals 0, then we just want to return 0, right? So I'm gonna do it this way. if n does not equal 0, then we can go down this path where we go, the stepper gets initialized, and for as long as n is greater than 0, sorry, as long as n is greater than 1, so if it's already 1, it just stops, because we got here, because it's not equal to 0, if it's 1, we just skip this. If it's greater than 1, we have work to do. And what happens is we go, okay, if n bit mask 1 does not equal 0, right, so we need an accumulator as well. So this is interesting. S is the stepper that's going to be squaring. So I want another one that's going to be called A. It starts off at zero, 1, 1 as well, I guess. Let me think. If I have 0, 1, 0, that should work. Right, if I have, wait, no, that's not right. It should be 1, 0, 1. So this is kind of weird. If I have 1, 0, 1. Oh, okay, okay. We're getting there. We are getting there. Just things to notice still. More and more specific details. So, if I have a matrix like this, 0, 1, 1, 1 to the k, what that gives me is how I apply the Fibonacci step k times. If I'm applying it once, if I want to find Fibonacci of 1, then this is my result, right? If I want to find Fibonacci number 2, then I square this, and the result will be in that spot on the squared version of the matrix. So, squaring that gives you, just to make this more clear, 0, 1 times 0, 1 is a 1 there. 0, 1 times 1, 1 is a 1 there. 1 there, 2 there. So we get that. But Fibonacci number 2 is still 1, and that still gives us the right result. Fibonacci 3 is living here, but we don't care about that. What we care about is if we were going to get 3, we would do this matrix, right? We would cube it, and that would lead us to this matrix, and then we would take this one, and so on and so on. Now, what if k is 0? Well, in the matrix form, that would mean we should have the identity matrix, right? When you write something to the power of 0, you get the multiplicative identity. That's this guy right here. This makes a lot of sense, like in terms of Fibonacci numbers. This would be like f of -1. Technically, like if you look at the Fibonacci numbers 1, 1, 2, 3, 5, you can figure them out backwards. So 5 minus 3 is 2, 3 minus 2 is 1, 2 minus 1 is 1, 1 minus 1 is 0, 1 minus 0 is -1. Sorry, 1 minus 0 is not -1. 1 minus 0 is 1. So like this is like f of -1 right here, right? So that makes perfect sense. The identity matrix is the same thing as putting a 0 right there. So we can make a stepper. We can make a valid stepper that looks like this, 1, 0, 1. Okay, so then when we're done, the result we want will be the one that's right here. And then that's our accumulator. Here is our stepper. This one should be, this is the one we square, so this is 0, 1, 1. And then what we're going to do is figure out how to write the loop. So for as long as n is greater than 0, do the following things. First, we take a look at if the low bit of n is not 0, then we need to take what's in the stepper, Because that would be like if our number is, written in binaries like 1, 0, 0, 1, 0, 1. If that guy is a 1, then the current value of the stepper needs to get multiplied in. So we then do multiply a s. We multiply that into the accumulator, right? Then what we do is we take n and we bit shift it 1. So then this gets dropped out, right? We get left with this. And on the next step through, we'll see this 0 and we won't put it in. But we also want to increment the stepper, because if this was the 1 spot, then this is the 2 spot, right? So when we get to here, we're going to be on the 4s spot. And when we see that one, we're going to want to be accumulating in the thing that's the 4th power. So we have a 1st power on the 1st step, a 2nd power on the 2nd step, a 4th power on the 4th step, an 8th power, and so on and so on and so on. So we then do square the stepper right here, right? And then it'll check if n equals 0. Okay, so we could do this even more efficiently in assembly, because we won't be trapped with like the control flow as it's written here. But we could like not bother doing the squaring if we're already done with the loop. But then we'll come back up here and check the bit again, do the accumulation if necessary, and so on, until n gets small enough that we're done. And then when we're finally done with all that, the accumulator has our answer. Result equals accumulator position 1, and we return the result, right? That's the whole idea here. So there's our pseudocode. That's pretty straightforward. All right. Let's get into it now. So first things first, we want to establish those steppers, the accumulator and the squarer. So we need to do RSP plus, let's see, it's 8 times 6. So that's how much is that? 8 times 6. Right, 48. So we're going to add or sub RSP 48, and then we'll add that back in later. At the value RSP, we're gonna have to just move some values in here, right? So RSP 0. Wait. We'll make the first one the accumulator. And we'll make the second one, suppose I should make those maps like that. Since I'm moving a constant in, and I'll need to know how big the constant's supposed to be. Hopefully that syntax will work. 16, 32, the Q just tells it how big it's supposed to be. It's usually optional, but I don't think it'll be able to infer this time. 16, 24, 32, 40. So 24 is the beginning of the squaring one. So that one starts at value 1. This one starts at value 0, right? This is our accumulator. This is our so this is like A equals 1, 0, 1. There's the accumulator. This is like squarer equals 0, 1, 1. There's our squarer. Okay, so what was the next thing we have to do? So we want to check. So for an unsigned value, we can just check if it's equal to 0. So we're going to do test. RCX should do the trick. Jump if that is 0 to the label done. I don't know what syntax to use for jumps yet, do I? Calling convention, proc directives. Does this tell me anything useful? It's a new label by assigning the current location counter value and the given to name, label, qualified type. Let's yeah. I think this is the one I want. Proc. All right, we'll try it. Done. Label. Let's see if that works. What do you think? Okay, so mob queue doesn't work, so that must be AT&T only. This maybe needs to be like, is it like H? Is that how we tell it? No, cannot remember. Is it like this? Does this tell it? How do I tell it? Doesn't really clarify. How do you? Okay, we just need to look this up. x64 Intel syntax 64-bit immediate. Syntax. talking about here? Okay. There it is. Got it. So I need to come over here and say keyword footer. So that'll let me tell it how big or right I want to do at that location. Very good. Now, how do I do MASM jumps labels? Show me. Not inline assembly. MASM. Okay, so this is not using the label macro. It's just a colon, jump equal, and then the name of the label. Okay, that's easy enough. Let's try it that way. Perfect. Okay, there we go. We are gonna wrap up now. We are past the 4-hour mark, so I'm gonna have to cut it off. But let's get this problem done. You know, it's almost close. We've been fiddling with syntax and getting things working a lot this time, which was what I expected. But we are very close to being done with problem number 2, which would be quite good progress. So let's see, Fibonacci number. We're going to take the n. We've set up these things. We tested RCX. If it's 0, we jump to done. At done, we move into RAX. The value at RSP plus 8. That's our final answer. And then we want to grab, I think, let's see. So this is going to be the part of the algorithm where we do the if. I want to grab a pointer to the accumulator and the S. So the accumulator is at RSP. So can I just grab here we're going to do R8 equals points to S. So that's just going to be load effective address into R8 RSP plus 24. So R8 points to S. And then we're going to do the if part right here. So we want to find out if that low bit is set or not. And there's a cool trick we can use for that, I believe. How can we test the parity bit? Where are my jump instructions? Do I not get to see jump instructions here? F, E, F, G, H, I, J. Jump. Jump if condition is met. This is the little stuff I want. JCC. So I want wow. Who knew? Jump RCX 0, ECX is 0, CX is 0. Carry bit. Where can we look at parity? JP and JNP. So parity bit will be 1 if it's odd and 0 if it's even. Okay. So what we do is if n and 1 equals 0, go to skip accumulator. So we test RCX. Oh, we still have to test RCX in there. So weird. Do I ever... Yeah, I'm gonna have to redo the test, I think, because I might not have to redo the test. That would be kind of neat. Let's try and see if we can not do the test. So jump if not parity bit. So if the parity bit is set to 0, that'll mean that this... Oh, so if it's not 0, no, if it is 0, I want to skip. So if it's not parity, so if it is 0, then it's not parity, right? Not parity is 0. Okay. Then we go to skip accumulator. Now we'll put skip accumulator over here. And then we're going to do the accumulator logic. The accumulator logic is this. The accumulator logic is this guy right here. We call the mul function with the a and the s. So call Fibonacci stepper mul, but we need to set the parameters. So RCX has to be changed to RCX. So we move into RCX our accumulator value, which is RSP. We move into RDX what we have in R8. Why do I do it that way? Skip this. What we're gonna do is say LEA RSP plus 24 anytime that comes up. That way I don't have to store it in an extra register. So we just say, here are the things I want you to do a multiply on. But that means I'm going to be throwing out the RCX value, which is a problem. So we're going to use RAX as our N. Instead of RCX. That way, because RAX we don't have to return during the loop at all, so we can use our RAX as long as we want, and RCX can get tromped over here. If we're 0, we're done. If we're not parity, we skip the accumulator here. We do the accumulation. So call, first parameter is RSP, second parameter is RSP plus some extra. That's where the accumulator is in the destination slot. And let me double check this. The way I wrote it was, yeah, the destination slot second. So accumulator in the first argument, the source in the second argument. So there we go. That doesn't really work either, does it? Because REX is caller save. So what I should probably do in this case is something like use a call save register, and we can push RSI up here, pop RSI right here. So callee just saved RSI, and then we use RSI here. That way, this guy here, the call to our helper Fibonacci stepper mul, isn't an issue that will mess up our loop. So we test RSI, go to done if it's 0. We skip the accumulator if it's not got parity. Then it's an even number, and then we do this stuff. Then let's see, what do we do next? So this is where skip accumulator happens. Let me look at my, okay, we bit shift. So this is shift right RSI 1. So here's a question, does that change? shift right, modify the SF, CDF, and PF flags are set according to the result. So that'll give me a new value in my parity flag and my 0 flag. I shift right by 1. Now what I can do is repeat if my condition is met to end, then I can be done right now. JZ done. And I don't have to do an extra test because the test is just for setting the flags. The shift does the flag setting this time. So that's good. And then we square this. So there's like an early out that we're doing here to get us out of the loop. Instead of having to square something that we're not actually going to use, we check it first. So if we didn't skip to done, yeah, here's my skip accumulator. If we didn't skip to done, then we want to square S. So we set RCX to RSP, I believe. Or that might be wrong. I think we set it to load into RCX RSP plus 24. This guy here. And we call Fibonacci step or square. That should square S. And then we jump unconditionally back to here. But I don't think we can, we don't really want to assume after a function call. Yeah, so here we don't need to do an extra test. It's true. But here I think we have to do an extra test. And the reason for that is that after the function call, I don't think we want to assume that the flags still have whatever was in them. You can't really go that far, right? So here we'll jump back to loop. Loop will start right here. And it will go test RSI again. So another way we could do this is start the loop here, drop the extra test, skip accumulator. So it seems overcomplicated. Like I was thinking we could avoid an extra test instruction here at startup. And the way we could do it is by saying, well, we know, yeah, so we know right here that we have the flags where we want them. And if we didn't jump to done, then we are still going to have to square. But before we call that, we could use the flags we have to remember whether or not yeah, I think testing it again is just better. We could test it again down here. To make that the loop. No extra test the first time through. But then here there's a test and an extra jump instruction. And the jump instruction says, hey, if n and 1 equals 0, go to skip accumulator. Otherwise, you go to loop, right? So the idea is like, this thing here only ever gets reached if you don't hit one of these J and P things. And then once you do hit it, it flows into the thing that always has to happen. So skip accumulator is just a way to jump into the loop without doing the accumulator part. So here, you do the test, you reuse that test here. Here, you can't reuse the test from before, so it's different code. We can't reuse this code if we want to keep this from having to double up the test instruction. But later on, we would need to double up the test instruction, so it needs to be a separate path. And then it has a chance to skip the accumulator, or it can go to the top and do this part. And then it does the accumulator, does the post-accumulation part the same every time. I think that's good. I think that's good. All right, maybe I shouldn't use the word loop. You're not gonna like that, huh? Can I call it loop 0? This is a mistake. Okay, so that looks pretty close to done. See if we can get a Fibonacci number. Let's get the first one. We get a 0. That's not right. All right, let's step through it. Okay, so I'm gonna want to see in our U64 RSP 6. Right, you know about this one though, right? 101011. Very good. RSI. Test. Let me look at their registers real quick. Parity flag is 0. We just tested RSI. What's in RSI? 1. I would have thought the parity flag would be 1, but it's 0. Okay. I need to go maybe see if that needs to get flipped. That skips the accumulator. We shift it by 1. Now the parity flag. Okay, so I got the idea of the parity flag wrong. The parity flag is 1 when the low bit is 0. It's a little weird, but okay. So jump, not parity, should be jump parity. Okay, so let's see. We tested RSI. RSI was 1, so we have a parity flag of 0. Jump parity, we don't jump parity this time. So RCX gets a copy of RSP. RDX gets a copy of that plus a little bit more. We call into that function. Here we're just doing a bit of work to multiply things. Comes back out. RSI 1 gets shifted to the right one. Jump of 0, it's 0. Move into RAX, the value 1. Decrease RSP, pop the RSI value. Return, now X contains a 1. Print that. We see 1, okay. So that looks more correct. Let's try and find out what the second Fibonacci number is. 2. What's the third one? Sorry. What's the third one? 1 again. Okay. Let's take a look at that. RSI has our 3. After test, the parity flag is 1. That's not working the way I thought it did. Let me check this. Okay, I thought it just looked at the low bit, but it sounds like it's maybe more like a hash. If that's the case, then it has nothing to do with what I want. So let's take a look at what else I could be doing here. I think that'll actually simplify the code because it'll just make sense to do this. So we're going to test RSI again, but we're not going to test it against RSI. We're going to test it against 1 because this is like a bit flag. And then we can just say if that is 0, we skip the accumulator and we put the loop right here. So now the test is different anyway, so we run it every time. Down here, we just go up to it. Let's see what happens when I do that. So the third one should not be 2, I don't think. Well, maybe it should be. 1 is, yeah, so 1, 2. So what we could do here is go, look, assert that Fibonacci number 0 is 0, and also just make sure that for the first 50 values you look at, the Fibonacci number I is equal to the Fibonacci number I minus 1 plus the Fibonacci number I minus 2. Go away for a second. Boom. Okay, so no, that is all correct. So our Fibonacci number function works. It gives us accurate results. So now we can answer some questions. First, our question was, is the Fibonacci number 33 or 34 like in the right ballpark? So let's see, this one here is smaller than 4 million, and this one is larger than 4 million. Okay. So 33 is the right one, and if you notice, let me just show you again, this is even. So another way we could look at it is this is a multiple of 3. So we know what we want to do, right? We want to, let's go back to our goal. It's the algorithm we worked out. Right, so this is how we did this part. What is done over here. So, where we started, our goal is to find this, the sum of all of the even Fibonacci numbers, or every third Fibonacci number, right? Every third Fibonacci number is even. The question asks for the sum of the even Fibonacci numbers with values under 4 million. So we want to compute something like this, and we determined that the even part is equal to the odd part if you take it in triplets, right? Every time you're looking at multiples of 3 in terms of your Fibonacci index, you get that the odd values and the even values have the same sum. So if you sum all of them, you get the odd ones and the even ones. So the sum of all of the Fibonacci numbers is exactly twice the sum of the evens. So the thing I want, the sum of the evens, is half of the whole sum. So if I get the whole sum, I'm done. So then we worked out how to get whole sums. That's what we've been doing for a while. And we just wrote all the code for it. And it looks like it's working. So I can get whole sums. Well, technically I can get Fibonacci numbers. So let me go over here where we wrote down how we get, right, here's how we get a Fibonacci sum function. So the sigma function over the Fibonacci function is like this, right? So let's go do that. Fibonacci sigma Fibonacci number Fibonacci sigma proc Fibonacci sigma NP. So this is just where we take, let's see, RCX is our n. We want to do RCX plus 2. We want to call Fibonacci number. We want to do sub 1 from REX and then return, right? So we're just computing the Fibonacci number of n plus 2 minus 1. That's all we're doing. So there's a Fibonacci sigma. And we just want to apply that to 33, I think, and then divide by 2. So if we've done everything correctly in the math, hopefully if the math is wrong, then it was all based on nothing. That should be our answer. Let's try this. I might not be signed in anymore. I am. Okay, cool. Check. Hey, that's it. Awesome. Alrighty, so I think that is it for now. We've solved 2 problems so far and got a lot of experience already on writing. How many? We wrote 168 lines, plenty of white space, but 168 lines of assembly. Just let's go ahead. We don't need to keep these around anymore. So those are ready to go away. But here's the library of stuff we've got written so far. We can get triangle numbers using the straightforward triangle number formula. We can get Fibonacci numbers using like exponential, like a squaring algorithm thing, which is pretty cool. The math behind that was something neat, and doing it in assembly was fun. It's probably not the most efficient assembly it could be. I have a feeling that if we stared at some of these things, there might be opportunities to avoid extra loads. But like I was saying when I was writing it, I really don't know. I have to go and do some research to find out if these things are inefficient the way I'm doing them. but I've done my best to follow ABI rules and stuff. I think I've done a good job at that. It looks like it's working so far. So we got a cool little library of a few math functions written in assembly. We will pick this back up in 2 days on Thursday with well, just the next Fibonacci, or the next Project Euler problem. So yeah, this was a lot of fun, and thanks for anyone who has been hanging out. I'll see you guys around.